Hey everyone, welcome to the first session on optimizing deep learning models using PyTorch Quantization by Multicore. We are proud to share that Multicore has been recognized as a great place to work for 3 consecutive years, a strong reflection of our culture of innovation and excellence. I'm Alicia Jagannath, your host for this session. I work as a senior software engineer at Multicore with around 4 years of experience in AI industry, actively contributing to a center of excellence. Let's get driving. So in this session, I will be covering the following topic: an overview of neural network, what is quantization, what is relevance, numerical representation of weights in memory, different types of quantization like symmetric as well as asymmetric, per-channels and per-tensor quantization. Finally, I will be covering the workflow, including post-training quantization as well as the quantization workflow. So, which include the code base also. Before getting into the topic, let me give an industrial outlook why we need quantization. So, as deep learning models become more complex, deploying them on edge faces unique challenges. So, quantization bridges the gap by converting the high precision models, typically float 32, to lower precision models. We significantly reduce the memory, increases the inference speed and lower the power consumptions. Through this session, we will explore how quantization works. So you can see a multi-layer perceptron on the left hand side image. The input layers, hidden layers and output layers. The typical transformation function built for building block of neural networks. Y is equal to Wx plus B, W being the weight vectors, X being the input and B being the bias, and we will obtain the output vector Y. So on the right hand side you can see that the output of this transformation will be passing through activation functions. So we have different activation functions, ReLU, sigmoid, depending on the scenario we can apply. So typically between these neurons, it is represented using a floating point, which increases the computational cost. So this is where quantization comes in, reducing the precision of these weights and activations to make model run much faster on the edge. So quantization does the process. For example, if we have a 7 billion parameters in a deep learning models, it will take around 280 gigabytes in memory, which reduces the speed on edge. So by quantizing the model, it offers smaller model size, which in turn faster on the edge, typically in the CPU, GPU and NPUs. Lower the power consumption, which is very much important for our mobile devices and embedded systems. In effect, we can leverage the hardware efficiencies. Like int 8 will be much faster than the float 32. Let's see how we can represent this float 32 in memory. This is a standard IEEE 754 float 32 format. The first bit is same as sign bit. So if the number is positive or negative, which says that. Then comes 8-bit for exponent, which is actually the scale of a number. It is stored using a technique called biased. So here the bias is 127 to actually store both the positive as well as negative values. For example, if we have exponent value as 5, we have to add with 127, so it makes 132. So we have to represent 2 to the power equivalent to 132. Then comes the Mantis part, which takes 23 bits. It represents the precision of a number. The actual number will be normalized, meaning it starts with a leading 1, which will not be stored but followed by the fractional bits. So let's discuss the formula here. Minus 1 to the power s is as discussed, it will be 0 if it is positive number and 1 if it is a negative number. And the mantissa part is 1.f. F is a fractional part. So it's always normalized with 1 before the decimal point. And the exponent is 2 to the power e minus 127. So e minus 127 will be represented in the exponent part. Let's see an example. Here 85.125 is our decimal example, which will be represented equivalent in a binary format. We will normalize it, keeping 1 as it is, and the rest will be taken to the fractional part, which makes it 6 decimal points. Sign bit, since it's a positive number, we will consider 0. So consider the bias exponent 127 plus 6, which will give 133. So 133 decimal equivalent will be equivalent binary I have represented. Altogether we will store in the memory. One more thing to mention is that after the fractional part representation, we will fill with zeros to cover up the 23 bits. Now let me give an high level overview where exactly the quantization fits in. This gives an idea. Given the deep learning models, normally in the float 32, we have to pass through our quantization to lower the precision, typically int 8, int 16 also. Once this lower bit models are available, we will be passing it to run on the edge. We have edge devices like we can run on CPUs, GPUs and TPUs. So on CPUs, we have x86 edge devices. We can use Raspberry Pi. GPUs, example NVIDIA Jetson Nano, and in TPUs we have Qualcomm SoCs. Now let's see different types of quantization. So when I say different types of quantization, how we are mapping the float 32 to int 8 is what exactly means. So we start with the symmetric quantization. Symmetric quantization, as the name suggests, it's a symmetric around with respect to 0. It doesn't have an offset. So the alpha and beta, which is min-max range, will be considered as the absolute max value. Let's see an example here. So given these data points, we will find the alpha being 8.59, which is the maximum absolute value. Next, we will calculate the scale factor. Since it's normalized around 0, 127 divided by 8.59. To achieve the quantized value, we have to multiply our inputs with the scale factor by rounding off. This is our final data points will be. Now moving on to the asymmetric quantization, the min-max value from the floating range will be the min-max value of the quantized range also. So alpha minus alpha and beta will be max and min values. So in this case, the data we assume is not normalized across 0. We do have an offset, 0 offset value. Let's see an example. These are the inputs. So alpha being the 8.59, which is the maximum value, beta minus 6.48, which is the minimum value here. So scale factor here, since we are taking the full range, it is 255, and alpha minus beta will be divided with. So we will get around 16.93 approximately. So apart from the symmetric quantization, here something called the 0 pointer offset. So we will, how it is calculated is beta into the scale factor, rounding off. Finally, to get the quantized data points, we have to round off with inputs multiplied with the scale factor, which is similar to the symmetric quantization, and an extra addition of the offset needs to be done. So this is the final result. Now moving to the per-tensor per channel. So different quantization parameters will be applied to each channel of a tensor. So that is per channel. The scale and offset is different for different tensors. We can call it a per channel. If across the tensors we have only one scale and offset, we'll tell it is a per tensor quantization. This is good. Per channel will be good mostly in case of more of convolutional layers. Now let's see what is calibration. So it's a process of choosing the min-max value alpha and beta from the data points. So pre-processing steps usually done during the post-training quantization. So determines the value of each tensors. So how it is done is we will run a few batches of data and collect the statistics. There are different methods, min-max method and percentile. Use this to set the scale and 0 point. This avoid unnecessary quantization errors. On the right hand side image you can see min-max method and also percentile applied. So the input original data, you can see there is an outlier 9,999. So when we are trying to apply the quantization using passing through the calibration of min-max range, you can see 5.49 when quantized it is 3.94. So the higher error rate we can get. At the same time when we are using percentile method, it's 4.17, which is actually very less error. So going forward with the percentile approach will be much better. Now let's see a general workflow of a quantization. So first we have to prepare the models. It should be just chit traceable. All the modules should be able to pass through the quantization. So we will insert the observers of a quantized modules. For this will collect the statistics for quantization. So calibrational training, that depends. If you are using a post-training method, we will use the calibration. If it is Quantized-Aware, then we will use a training. So allows us observers to collect the statistics. So if it is training, fake quantization to learn the quantization parameters. Finally, we will do the convert the model to quantized one. Now let's go through post-training quantization. So here to give an overview, it is applied before, it is applied after the training is done. So any kind of pre-trained model we can pass through the PTQ or post-training quantization. So only a few data set is needed to calculate the statistics. So this is much more easy, or computational cost is very less compared to the QAT approach. Let's go through the workflow. So we will get the pre-trained models. We will fuse the modules, like if we have convolution and batch norm combination coming sequentially, we will fuse this. This is in order to reduce the model complexity, and then we will insert the stubs and observer to calculate and store the statistics. So parallelly the calibration data will be passed through the calibration. Finally, we will do the quantization and we have the PTQ model output. So output will be depending on which methods. Since we are using PyTorch, it will be either ONNX format or PT format that we can make it. Let's go through the code and see how it is made. So I have taken the example of MobileNet, and I'm importing all the packages. So this code is taken from the official website of PyTorch. And the addition has been replaced with nn.quantized.float functional. And we will insert the const stubs and decons at the beginning and end of the network. Let's go through the code base here. This is the architectural definition, which is exactly given in the PyTorch website. This is initializing the model. Let's go through the forward function. So you can see the self.const, which is actually inserting the const stubs, and finally we are dequantizing it. Also, one extra function has been defined. This is to fuse the models. As I discussed, if convolution plus Bashnum is there, we will fuse it. Similarly, convolution plus Bashnum plus grade also will be fused together before quantization itself. So evaluation function, this is very straightforward. Just checking the accuracies and evaluation. Again, data preparation, this is also pretty straightforward like any other model. So let me save this model in .pt format. You can see how the model is. Okay, then coming back to our, first we will determine the baseline accuracy, which is float 32 accuracy. So we have loaded the model, prepare the data set, and finally I am doing the evaluation. Also after fusing the models, and let me show you the results. So this is before fusion and after fusion, how the Bashnum can be. Here you can see the convolution and Bashnum has been fused together in the second model. Okay, so the baseline, when I am executing the baseline, the model size is, original one is 13 MB, and evaluating over 10,000 images, the accuracy is 83. Now let's go through the PTQ method. So here I have doing calibration 32 byte size. It's loading the model, turning into the evaluation mode, fusing the model. Here I am just inserting the default configuration, not passing any particular quantization method like per channel. By default it will be Per-Tensor quantization methods. Okay, let me evaluate and show you the result. Conversion is happening. So something to mention is the calibration. Here we will be doing the calibrating the data set. Okay, so here you can see the parameters are printed. It is Per-Tensor symmetric method. So finally you can see the accuracy is 78, but the model size has been reduced from 13 to around 3 MB, which is really small. But the accuracy drop is a bit huge, as is initial 83 is a baseline. Now coming back, dropping to 78 is not much acceptable. Let's insert Per-Tensor quantization here. So while passing through per channel quantization, you can see on the 10,000 images it improved from 78 to 80. But still it is not enough. So let's go through the QAT methods. So since our post-training method accuracy drop was bit more, we can try the quantization-aware training. So quantization-aware training is quantization-aware training, quantization is simulated during the training process itself. So it uses fake quantization ops, and we have to tune these parameters while training itself. Compared with the post-training, the computational cost is really high, but QET will yield better accuracy than PTQ. Let's see the workflow. If the already pre-trained model we will take, then we will fuse the modules, which is similar in the PTQ method also, insert the stubs and observers. Here we have to train and fine-tune the data. finally we will do the quantization. So let's see how in code, let's walk through the code how it is being performed. Okay, this is a training function. This is also pretty straightforward. In the images and target, a model will be passing through, calculating the loss. So we will load the model, use modules similar. So here you can, when I print the model, you can see here weight, fake, count ops are inserted in the middle. Let's train for 20 epochs. So see, so here we reached, though the initial accuracy was 17, it progressed up to 83, which is without any drop in the accuracy. So this is how QAT works. So it needs the resources, GPUs, CPUs according to the quantization, according to the number of, if the number of images are more, then it needs much more resources. By this we came to the end of the session. Thanks for watching. Hope this find insightful. Do connect with us through LinkedIn, YouTube and all. Thank you.